Hi guys, this is Dr. J, and in this video we are going to talk about hydrogenation of alkenes, which is basically a reduction reaction for alkenes. So during hydrogenation, we are adding hydrogen atoms to the sp2 hybridized carbons, which is basically the double bond or even triple bonds. Okay, so addition of hydrogens to double bonds or triple bonds uh, uh, is using hydrogen molecules is called hydrogenation. So this hydrogenation reaction is considered a reduction reaction. So in chemistry there are two types of reactions, oxidation and reduction. So hydrogenation is actually a reduction type reaction for carbons. Why? Because you are adding hydrogens to carbons, so therefore that is considered reduction. So if you don't remember what is oxidation and reduction, so basically oxidation and reduction are directly opposite to each other. So oxidation and reduction are directly opposite to each other. And during oxidation, atoms lose electrons. Typically during oxidation, you can see a loss of electrons. So reduction is the opposite. So it will be a gain of electrons. So similarly, oxidation can be defined as adding oxygens, okay, adding oxygens, and reduction can be defined as removing oxygens. And oxidation is also defined using hydrogens. During oxidation, you remove hydrogens. And during reduction, you add hydrogens. So in organic chemistry, tracking oxygen and hydrogen is actually very practical as compared to inorganic chemistry. Why? Because in organic compounds, it is always common to have hydrogen and oxygen. So if you could track what happens to oxygens and hydrogens, you can easily identify oxidation and reduction. So in hydrogenation, what we do is we add hydrogens to carbons. So if you are adding hydrogens to carbons, that reaction can be considered as a reduction reaction. So basically once again, hydrogenation is considered reduction. Why? Because you are adding hydrogens to carbons. So adding hydrogens is actually considered hydrogen is a less electronegative atom as compared to carbon. So whenever you are adding a less electronegative atom to carbons, you are reducing carbons. Okay, you are reducing carbons. So once again, we do this hydrogenation to alkenes as well as alkynes, but in this scope of the video, we are going to talk about alkenes specifically. So you need to have your alkene product. So this is your alkene. In here I have 1,2-dimethyl cyclohexene. Okay, so this is your alkene, and then hydrogen is added to alkenes in the presence of a metal catalyst, such as nickel or platinum or palladium. Those are the most common catalysts for the hydrogenation, and in this reaction we are using platinum dioxide. Okay, so that is the catalyst. And then what happens is that you will get rid of the alkene double bond, and then you will add two hydrogens to each of the sp2 hybridized carbons, the good thing is that you don't have to worry about Markovnikov rule. Why? Because you are adding uh, the same atom to both carbons, so you don't have to worry about the rich carbon or the poor carbon and then Markovnikov rule. So there is no need to worry about Markovnikov rule. But we have to worry about the stereochemistry of the reaction, especially if you have a cyclic compounds. So something that you need to keep an eye on is cyclocompounds. Excuse me. Something that you need to keep an eye on is cyclocompounds. Okay, why? Because if you have cycloalkenes, then stereochemistry could be important, because hydrogenation adds hydrogen according to syn stereochemistry. This reaction works according to syn stereochemistry, which means the two incoming hydrogen atoms are going to be on the same side, like cis. Okay, so the two hydrogens are going to be cis to each other. So therefore it is very important to keep an eye on cycloalkenes, because the product will have two hydrogens in syn stereochemistry. So here is another example. Okay, let's do another example. Okay, so let's say we have something like this. Okay, so this is our alkene. Okay, this is our alkene. Okay, and for this reaction, let's use hydrogen and some catalyst. We can use platinum dioxide, or we can use palladium carbon. Or you just need a catalyst, okay, a metal catalyst. And then what we do here is that here is the starting material again. I will show you what happens. You will get rid of the double bond. And now both the sp2 hybridized carbons, which is this one and this one, both these carbons lost a bond. So you have to give something. So what you give in this reaction are hydrogens, right? So both carbons will get hydrogens. But here's the thing, in skeletal structures we don't show hydrogens, so you don't have to show where the hydrogens are. Okay, so you can simply erase the double bond and you get the product. Okay, so which is very straightforward. Okay, so you simply have to erase the double bond from the starting material and you get the product. So hydrogenation is an extremely easy reaction to understand, especially if there are no cyclic alkenes involved. Let's take another example. Let's take cyclohexene. And then we will have a couple of substituents in here. We will have two methyl groups or two chlorines. Okay, whatever, it doesn't really matter. Okay, so if you try to hydrogenate this reaction, you put hydrogen and then let's put palladium carbon as the catalyst. Okay, so here is the starting material, but this is a cyclic compound. Okay, this is a cyclic compound, so or it's a cycloalkene. So you need to worry about the stereochemistry. First of all, you are getting rid of the double bond. Okay, and then you will put the two hydrogens on the same plane or same side. Okay, so if you use a wedge to show the hydrogens, you will have to use a wedge to show both hydrogens. Okay, make sure to have both hydrogens on the same side of the ring. Okay, and this is your product. Okay, so you can draw it like this, but make sure to use either the wedge or the dash to show both hydrogens. Or sometimes you don't even have to show hydrogens. Okay, you simply have to draw the chlorines correctly. And in here the two substituents will be on wedge. Okay, So very easy. Okay, just keep an eye on cycloalkenes. If you have a cycloalkene, it could alkene. The stereochemistry could be important. Okay. All right. So let's go to the next slide. In here, I have the mechanism. I mean, this basically explains why the hydrogens are added according to syn addition, okay, or syn stereochemistry, okay. So, as I mentioned earlier, for this reaction, you are going to need a metal catalyst. That is the key here, okay. You're going to need a metal catalyst, and then the hydrogen molecule. This right here is your hydrogen molecule, okay. Hydrogen molecule is going to be adsorbed into the metal, and they are going to break, they are going to break the bond between the two hydrogen atoms, okay. So as you can see, there is no bond between the two hydrogen atoms, okay. There is no bond between the two hydrogen. I mean, you used to have a bond, but now you don't, okay. Instead, the hydrogens are adsorbed, okay, surface adsorbed into the catalytic surface. And then here comes the alkene, okay. Here comes the alkene. This is your alkene. And then the alkene is going to break the double bond, okay, on the metal catalyst, and then it is going to attach the two hydrogens from one side. It is going to, alkene is going to attach the two hydrogens from one side, okay. That is why the hydrogens are added according to syn stereochemistry. That is the keyword, okay. Don't forget that. But I mean, this is, since stereochemistry is irrelevant if you have mostly irrelevant, I wouldn't say always relevant. It is usually irrelevant if you have no cyclic alkenes, okay. No cyclic alkenes. I have a very nice example in the next slide as well, okay. So once again, according to this example, you can understand the sensitivity of this hydrogenation reaction towards steric environment, okay, steric environment. So in here I have an alkene right here, but this alkene is blocked from one side, or you can say the methyl group is blocking one side of the double bond, so the hydrogens can only attach from the bottom surface, okay, from the bottom surface. So therefore the hydrogens will be present in the bottom surface, okay, bottom plane. So you will almost never see the two hydrogens on the top plane. Why? Because of the steric environment, because of the steric environment. So keep an eye on these things, okay. Keep an eye on cycloalkenes, okay, or keep an eye on steric environments. Those are the only things that you have to worry about when you are doing hydrogenation reaction. Otherwise, it is a very straightforward reaction, okay. It is a very straightforward reaction. And in here I have some facts about hydrogenation reaction, okay. So this hydrogenation reaction is extremely vital in food industry, especially when you are making saturated fat from unsaturated fat. So basically in food industry, they take vegetable oils or different type of oils, and then they hydrogenate the oils to form things like butter, margarine, okay. So for the conversion process, or the transferring process from liquid form to solid form, which is the transformation of oil to butter, uh, uh, is done through hydrogenation reaction. So they basically bubble hydrogen in the presence of a catalytic metal in order to achieve this saturated fats, okay. So this reaction is extremely common in industry, okay, industry. And in biological pathways, they achieve biological hydrogenation using biological molecules such as NADPH2 and then sometimes FADH2, okay. Those are some of the biological molecules that helps the hydrogenation reaction in biological pathways. All right, with that, I'm going to ask you to pause your video and then see if you could do this worked example, okay. See if you could complete this worked example. All right, so when you are doing this worked example, it is very straightforward, to be honest, okay. So you just have to figure out the molecules that you have, okay. Let me use a different color. me use a different color. I'm gonna use, okay, maybe black. All right, so this is the I mean, I always like to use skeletal structures so that I don't have to keep track on the hydrogens. Okay, so this is the first molecule that you have. So when you wanna do the hydrogenation reaction, you will simply erase the double bond. Okay, you will simply erase the double bond. So basically erase one bond. Okay, erase one bond. So the answer will be this. Okay, this is your answer. Okay, very straightforward. And then for this one right here, okay, the molecule that you have is this, and then you simply have to erase the double bond, right? You simply have to erase the double bond. So I mean, even though this is cyclic, you don't have any substituents on the sp2 hybridized carbons, so you don't have to worry about the stereochemistry at all. Okay, simply erase the double bond and you get the product. I mean, you get the product. So these are the answers. Okay, once again, I recommend that you guys watch this video at least one more time and then get a full understanding of this very straightforward reduction reaction for alkenes. Okay, and here are the answers, but they are basically the same as what I showed you in the previous slide. Okay, all right, have a good one, guys. Take care.